and welcome to Universal Universe's first video. Today we'll be talking about Schrödinger's equation. But first, let's brush up on some basic physics. Let's talk about what everything is made of. Everything in the universe is made up of compounds and elements. Elements which can all be found in the elemental table, such as hydrogen, oxygen, bromine, all that kind of stuff. And compounds are made up of pairings of two or more of these elements. So you can have bronze, which is made up of copper and zinc. So then we have molecules and atoms. And these molecules and atoms are what form compounds and elements. Compounds are formed of molecules, and elements are formed of atoms. Millions and billions of atoms go into each element. And then these elements then combine to form compounds. So in that way, compounds are in fact formed of millions and millions and billions of molecules of copper and zinc to form bronze. Then, smaller than that, we have particles. And these particles make up every atom. So you've got the proton, the neutron, and the electron, which form together in different variations of density to form different molecules and atoms. Now that we've gotten that out of the way, let's move on to the branches of physics. So there are four main branches. There's classical mechanics, which deals with big and slow moving objects, such as the sun moving at a relatively slow moving speed compared to light. Relativistic mechanics, in fact, is with rather large objects, again as the sun, only this time hurtling at the speed approaching that of light. Then we've got, on lower level, we've got quantum mechanics, which deals with small and slow objects, which is to say, particles moving extremely slow due to their mass. And then we've got quantum field theory, which deals with protons and neutrons, mainly photons, moving at the speed of light or approaching it. Now that we've got that out of the way, let's begin with what led up to Schrödinger's equation. In physics, before Schrödinger's equation, everything used to be related to F is equal to ma, which is the equation for force is equal to mass times acceleration. You could use that to find at what place any object would be after a certain amount of time. This was referred to as Newton's second law of motion, and it only applies to classical mechanics, which of course back then there was nothing else. The only option was classical mechanics. There was no bigger quantum theory. There was nothing else. Except years of research showed that on the quantum levels, like particles such as neutrons and electrons, things behave much differently than on the larger scale, which meant that Newton's F is equal to ma would no longer apply. This meant we needed a new equation. And to explain this, picture a pool game. Using F is equal to ma in the real world, you could find out wherever any ball would go no matter how you hit it and where it would end up. However, on the subatomic level, if you had a particle and you hit it, you could theorize it's going to land in the first pocket after bouncing off another pool ball. However, in the end, the experiment would show that the particle ended up in your beer bottle. So in that way, F is equal to ma could no longer be used for anything. Alright, now we've got the introduction out of the way, let's move on to the waves and particles part of this. In classical mechanics, physicists use position and momentum to find anything they want about the state of the system, which is to say how a car moves, how the bowling ball game is going, that kind of information. So regular questions in classical mechanics will go something like, if we know how the system looked and began at time 0, what is its state? And then from that you get its evolution, which is if you hit a bowling ball this hard, where will it go and at what time will it be in what x position? This is quickly answered using Newton's second law and gives you all the information, everything you could possibly need to know about your system. It'll tell you aside from the mass, but that has nothing to do with the equation, as mass is nearly inexistent in a vacuum, which is space. However, on the quantum level, things begin to act differently. As I touched on before, in a pool game, your particle might end up not even being on the board, which is where it was theorized that light, which is a particle, in fact does not move like a bowling ball, but more like a wave, which is why F is equal to ma could never prove where it was, because they didn't behave like particles, they behaved like waves. Speaking of light, Maxwell and Newton showed us that light behaves like a wave, which is revolutionary because they had never thought of light behaving as anything other than a particle, and now it had been proved to move like a light. So in the 1990s, Maxwell Planck figured out light's equation for a wave, which is as opposed to using F is equal to ma, which was no longer functioning for light, Maxwell Planck figured the wavelength equation, which is the F is equal to ma of light. And this became E is equal to hf. In this equation, E is the energy, F is the frequency, and h was Planck's constant. And in an equation where you have a constant, the constant in fact never changes, it is constant. And the point is, it creates a balance ratio between the first digit, the first multiplication, and the last, which is if the energy of the wave of light rises, its frequency will lower. And if the frequency heightens, the energy will lower. And this is all because the constant never changes. So if you know basic math, when you have two things equal, you can divide to find the last, but that is only if the middle remains the same for both. So that's why the constant was useful, and in this case the constant was 6.628064 times 10 to negative 34 meters squared kilograms per second, which is a pretty big number, but it was basically saying that the light will always be the same. Now, with a little theorizing from Einstein, bam, light now behaves as a wave and a particle at the same time. This was revolutionary because physicists had never thought of something that could move both as a wave and a particle. And to picture this, if you picture a tsunami wave and then you picture sand, now they're the same thing. So now you have a tsunami wave of sand, which was revolutionary at the time. This meant that physicists now needed an equation for matter that moved both as a wave and as, say, a marble at the same time, which was never done before. And moreover, in fact, these states of matter were in fact divided into their own corners of physics. You'd had the classical mechanics, and then you'd had relativistic mechanics. They now had to be merged, which in fact tied in nicely with a quest from the 1800s, which ever since then physicists have been actually trying to bring together optics and mechanics into a way in which they both coincided, which is exactly what a wave particle needed to be from the optics, which is waves, and mechanics, which is particles, and they now needed to be joined together to find the equation for light. Then, the young French physicist de Broglie gave us even more to think about. He theorized, based on Einstein's theory of relativity, that not only light subatomic particles, which is to say photons, as that is all light's made of, could move with this so-called light bipolar, but also every subatomic particle. Every neutron, electron, and proton in the universe was theorized by de Broglie to be able to move as a wave and a particle. This was groundbreaking for physics. This meant that no matter what solid, liquid, or gas you had, it was either moving as a solid, as a particle, or as a wave. This would totally throw upside down the world of physics if proven. However, luckily for us, it was only theoretical for a little bit. Not but a few years later, de Broglie conducted a groundbreaking experiment, later called the double-slit experiment. He conducted this in two different ways. The first one was to prove the duality of light, so how light behaves like a wave and a particle. The second one was to prove that not only does light do that, but all subatomic particles. He tested this mostly on electrons. His first experiment, called the double-slit experiment of light, consisted of crudely, a box completely dark on the inside, with two small slits cut into the top where a beam of light was shone. But instead of having two small lines of light on the complete opposite side of the box on the bottom, what was found was there were circles of rainbows showing that light in fact refracted through the hole and bounced around like particles while having reacted like a wave going through the hole, through the slit. Next, de Broglie conducted this experiment with electrons. So what he did was he placed a divider crystal and then shot a beam of electrons at it with 4 receptors on the back. 2 directly behind the crystal, which is where it would go through a split cleanly in half, and 2 ones right next to those in case there was dispersion. Now, picture you throw an orange at a knife. It splits right in 2. Now picture you drop the orange into the pond. It creates ripples. What happened is the electrons hit the divider crystal, and then instead of shattering into 2 different rows, or into waves going towards all 4, it did both. It reacted as a wave by splitting towards all of them, but instead of creating ripples that would interact with each other, simply divided into farther particles, which proved that they behaved as both waves and particles at the same time. This was definitive proof that not only does light behave as a wave and a particle, but subatomic particles also suffer from this so-called particle-wave duality syndrome. There was no known physics at the time that could do anything with this. In fact, none of the equations relating to particles could even come anywhere near finding what F is equal to ma for this, which meant that we needed a new section of physics. Physics needed to be reinvented. In the next video, we'll be going over what Schrödinger's equation is and what it's made of. Thanks for watching Universal Universes.